This video will be looking at how to deal with two-sample um, inference. So we're first going to look at paired samples for two means. So questions you're usually asking are the two populations the same? Is the average height of men taller than the average height of women? Is the average mean weight less after a diet than before? You can compare these different questions, and this is what we want to do. I'm not going to go through all of this because, um, as you can see, it just talks about what this is about and how hypothesis tests work. We're going to talk about the hypothesis for two-sample paired t-test. Um, as every hypothesis test, you first state your random variables and parameters. There will be two of each. Um, then you're going to state your hypotheses. Again, they're usually that the means are the same. HA would be that they're different, or one's more than the other, or one's less than the other. You can also think of it, since you're looking at the difference, you can actually think of mean one minus mean two is the difference mean. And so you can actually talk about the difference in means is zero, the difference in means is not zero, or less than zero or greater than zero. You're going to then state your conditions. Now, if you're doing a paired test, it means you're collecting them in such a fashion that the values in one sample, a value in one sample affects values in the second sample. Think of this as if you've got weight before and weight after, or blood pressure before and blood pressure after, or height before you give a fertilizer and height after you give the fertilizer, or different things like that. Usually that's where we see paired, but you can also see it in if you're comparing the same grocery prices at one store and another. So anything that says this number belongs with this number is what we do with paired samples. To help us look at this, let's actually go ahead and run our setups. We can look at some samples that are actually paired. All right. So, um, here's a sample that actually is a data set that has paired information in it. So here we have jobs, and they are jobs that are in California, their mean hourly wage, and jobs that are in New York, also their mean hourly wage. And so we can sit there and think about the fact that a job type in one state may affect the job type in another state. A shampooer in one state will make the same amount of money as a shampoo in another state. A fast food person may make the similar things in one state as the other in relationship to each other. So if you have a doctor in one state, they're not going to be making the same as a shampooer in another state. They're going to be making relatively similar salaries. So that's why we can consider this one paired as an example. And you're going to collect your sample in these pairs. So that's your very first condition you have to have is you've got pairs of these. So you collected them in some kind of paired situation. The other thing to think about here is that a shampooer's mean hourly wage here, this number here, would actually be attached directly to the same number in New York. So that number and this number are tied together. They're not necessarily the same number, actually mean. They're not exactly the same number, but they're attached together. There's a reason to put them next to each other and talk about them. So those pairs are taken together. The population of the difference between those random variables is normally distributed is the second condition. And the way to think of this is that we can actually find the difference because we can pair them together. We can put these two values together. We can actually say this number belongs with this number, and we can subtract those two numbers. That difference will make sense to us. Whereas if you can't pair them, they don't make sense to talk about that. But you can talk about how much more does a shampooer make in New York as opposed to in California. So we can look at that difference and talk about that difference. And we want those differences to be normal. I don't really care about the individual random variable being normal. It's that difference I want to be normal. As always, the t-test is fairly robust to this condition if the sample size is large. So if it doesn't happen that we have this, we at least have that normal, that if we have a large sample, we're robust. Your calculations for this, you actually need to create that difference columns. You actually need to take your data set and actually mutate it so there actually is a difference column between those two variables you're working with. And it's that difference we're going to care about. And so you're going to find that difference before you draw your density plot because you need that difference to be able to draw your density plot. So we're going to find that difference. That's what we're going to do everything on. And then it's just like the tests we were doing before, the one sample test, because now you have one column of a difference. And so we run just a t-test of that difference variable. Again, you put your alternative if you need to, and whatever your data set is. If you don't need the alternative, if it's not equal to, then just leave it off. Okay. Then you have your conclusions and your interpretations. Similar things with the confidence interval. Everything exactly the same for the confidence interval. Nothing really changes there, except that you might have to put in your confidence level when you do the calculations. And then you have your statistical interpretation and your real world. Checking these conditions as before, you state how did you take your random sample? What process did you go through to make sure it was a random sample? You describe your sampling techniques. And then you would do, for normal distribution, you'd look at your normal quantile plot and your density plot. All right, so let's try a couple problems here. Let's look at determine if the following are independent or dependent samples. So you randomly choose 9 international college students and 12 USA college students and compare their GPAs. Well, if we think about this, there's no reason to say this international college student's GPA belonged with a particular value in the USA college students. And in fact, there's no reason that that one value would actually have any bearing on one of the values over here. So this would be an independent sample. Because independence means that one doesn't affect the other. If we do choose 15 men with high blood pressure and measure their blood pressure, give them a new medication and later measure their blood pressure again, there is a reason that that before blood pressure value would be related to their after blood pressure value. So there is a reason that we could compare them or put them together or pair them together. So this would become a paired sample or dependent or matched. They have different names depending on which one you want to use. All right, so now let's actually try a problem. Many people talk about how expensive California is, but there's also a discussion of how expensive New York is. The question is which state has a higher pay to adjust for the higher cost of living? The data set California and New York wages contains all medium hourly wages of common different occupations in California and New York. What I would like to do is take a random sample of size 50 from this data set. Notice this data set has 708 different values. So we're going to take a um, we're going to take a random sample from that. And we want to know, we're going to use this random sample to see if the mean median hourly wage of New York is different than mean median hourly wage in California. We're going to test at the 1% level. All right, so here's my data set. We're going to glimpse it. So I called it new. And this is a glimpse of this to show you kind of what the values look like. To show you what this data set was, I did create it up here. So I actually did some wrangling here. I had 2 separate files of California wages and New York wages. I actually did something called joining where I put them together in one. Then I cleaned their names. Then I selected certain pieces. I only wanted some values. And then I wanted to admit anybody who was no NA. So that's why this data set of this new is a little bit smaller than the other one. And when you open it up, you're going to notice I only have those few columns I wanted to choose. I don't have every single one of the columns that was in the original data set. It was too much to look at. It's just much easier to select just the columns you want to look at. All right, so now, and there's my glimpse showing you those things. All right, and this is what's called the code book, gives you an idea of what the different pieces are, so you know kind of what these are. This is for the giant data set, if you want to know what all those different pieces mean. We're going to first take our random sample. So we'll just call it wage to give it a name that we're going to be working with. We're going to use this new data set I just created. And then we're going to slice it with the size of 50. So there's my new one, has 50 observations and my 5 variables. We then need to create a new column. We're going to be adding a new column to this data set you just created. This new column will be the difference between 2 other variables in your data set. So let's talk about which variables we're working with so we know what we want to deal with. So let's go ahead and state the random variable and the means. So the first one is we have random variable 1. And it doesn't matter if you want to do New York or California. It doesn't matter which one's first. Let's do New York, median hourly wage. Now, what that really means is that they took a bunch of people that are, let's say, if I look at this data set again, we took a bunch of people that were pharmacy aides. And we then found the median of those people that were pharmacy aides, because not everybody who's a pharmacy aide gets paid the same. So that's why we're dealing with the median this time. Normally we can't measure a median, but that's what we did in that one. And then a random variable 2 will be exactly the same, but for California. So the California median hourly wage. Our mean one will be the mean random variable. I'm sorry, I should call that parameter 1. Our parameter 1 is the mean New York median hourly wage. And then parameter 2 will be the mean California median hourly wage. So now that I know I want to do it in that order, that's why I need to do this. So I knew how to mutate it. I'm going to create a new data set. Actually, I'm going to create my same data set wage. I'm going to use the data set wage. And we're just going to basically just add a new column to it. So we're going to mutate it. We're going to use the difference. We're going to call it the difference between New York, because that's 1, minus California, because that's 2. And I'm going to run this. Again, it doesn't look like anything happened, but if you noticed, we now have 6 variables instead of 5. If we look at this, you'll now see we have a difference column. So this is showing you how much more New York makes over California, because we're subtracting. So in pharmacy aides, New York makes less because it's negative. In child family social workers, New York makes more because it's positive. Okay. So now that we've done that, let's do our hypotheses. And so we have our null hypothesis, and we have our alternative hypothesis. And again, I always like to do the alternative hypothesis first because that is my question. So let's go back up to the problem and see what our question was. And our question was, if the mean median hourly wage in New York is different than the mean median hourly wage in California. That is my question. So that is my alternative hypothesis. If you want to write it in symbols, you can. You just have to define those symbols up here when you define your random variables and your parameters, or you can just leave it without defining it. Your null hypothesis is always equal. So mean median hourly wage of New York is the same as the mean median hourly wage in California. Now we can state and check the conditions. So in that sense, we would have a random sample. Oh, I don't want to put 1 there. We're just going to state we have a random sample of 50 pairs. Again, it's that pairs we collected. Because if you look at our random sample, if you look at our wages that we have in our sample, these are paired together. We have California and New York, California and New York, California and New York, all paired together. We have them for every single one of these jobs, those pairs. So we have 50 pairs of median hourly wages in New York and California is taken. Then we got to check it. Well, we did. We took a random sample. So a random sample was taken using RStudio from the larger data set. So we did that. We took our random sample. We know we did it because we actually did it. Now we're going to state the other one, and that is that the population of the difference in median hourly wages between New York and California is normal. And then we have to check that. So to check this, we're going to create a density plot and a normal quantile plot of that difference column we created. So we're going to do first our density plot, GF density. And we're going to do it of that difference column that we created. Our data set is that data set of wage. And of course, the title is always nice. The title could be something like difference in wages, in hourly wages, meaning median hourly wages. Between New York and California. And then maybe it might be nice to do an X laboratory. All right, so an X lab might be something like the difference in salaries. All right. Then I want to do the exact same thing with a normal quantile plot. Let's just look at this density plot. That does look a little normally distributed. There's a little bit of something here, but it does look pretty good. Let's look at our normal quantile plot, which is GF underscore QQ. And then everything else is exactly the same. Except I probably won't do the X lab, so we'll take that out. I like the lab that it puts on there for the quantile plot. And that quantile plot does look fairly linear to the very end, but looks fairly linear and looks pretty good. So I would say since the normal quantile plot or the density plot looks bell-shaped and the normal quantile plot looks linear, then the population, the sample, I should say, comes from a population that's normal. All right, so now we're going to get to our calculations. And our calculations, we're going to use it on that normal curve. We're going to do a t-dot test. We're going to do it of that difference column we made. So difference. Our data set is that wage. Since alternative is not equal to, we don't need to put the alternative statement in there, and we can just run it the way it is. So here is our one sample t-test. Our t is 1.68. That's not really big T. It is positive though. That's one thing to point out. It is a positive value, which means we did New York minus California. So New York looks like it might be higher just because that's positive, but my p-value is 0.09. So it's not a very high p-value. It's not, I mean, it is a high p-value. It's not less than 5%. So our conclusion is that we fail to reject HO since the p-value is greater than my alpha of 5%. I probably should make sure that that was my alpha level. So let's just go back up to the problem. It does say, it says it tastes at the 1%. So it even is worse. It's greater than 1%. All right. And that means our interpretation, there is not enough evidence to support that and again, what was my hypothesis? My hypothesis was that the gotta find where I had that statement. There it is. Where that my mean median hourly wage in New York is different than in California. That is what I'm trying to show. And that is the one I don't have enough information for. So all I can say is that there's not enough evidence to support, oops, I should enough. There's not enough evidence to support that the mean median hourly wage in New York is different than the mean median hourly wage in California. The next problem is doing the exact same thing, but this time we want to find the confidence interval. And the nice thing about the confidence interval is to show all the steps. We've actually just did them all. We did most of the steps. We actually we already stated, we stated our random variables and the parameters. We could copy them, or we can just say C hypothesis test. Or you can just go copy and paste them in here. You've already done them. You don't need to do them again. The next thing was to state and check the conditions. Again, we've already done that. I don't need to do it again. So I can just say C hypothesis test. Calculations, those we do need to do a little bit differently because we do need to check what our level is. It says to do it at the 1% level that's used in the confidence hypothesis test, but there's a little difference here. The confidence level is going to be 1 minus that alpha level. And since our alternative hypothesis was not equal to, it's just 1 minus your alpha level. If that was if your confidence level was a greater, if your hypothesis was a greater than or less than, then you'd multiply this by 2 because you're going to look at both tails. And one-tailed test only looks at one tail. But this was a two-tailed test because it was a not equal to. It's called a two-tailed test because we're looking at not equal. We can either be bigger or smaller. That's two-tailed. If we're saying we're just bigger, we're only looking at one-tailed. If it's just less than, we're just looking at the other tail. So in those cases, you have to multiply your alpha by 2. Here we don't have to. So 1 minus 0.01 is 0.99. So that's actually the level we have to use when we go to run our hypothesis test of our confidence interval. It still is t-dot test. It still is on that difference variable. Our data set is still the same thing of wage. And then we can say conf.level equals 0.99. We can run that. And we can see now here's our confidence level. Our confidence interval. Our confidence level is 99. Our confidence interval is that number there. So our statistical interpretation is that we are 99% sure, or I am 99% confident that the interval negative 0.82 to $3.58, because that's what these were. These are hourly wages, and those are measured in dollars. So I should put the dollar symbol on there. Contains the mean difference between New York and California median hourly wages. Because that's really what we want to know. We want to know, on average, how much more is New York over California, or how different are they, I should say. Our real world is going to do a little bit differently here. Because we did California first and then we did New York first and then California. Because New York is first and we're subtracting them, notice sometimes it's negative, which means sometimes New York was less. Sometimes it's positive, which means sometimes New York was greater than. And we're looking at that difference, that mean difference. So on average, or we could say the mean, median hourly wage in New York is anywhere from 82 cents less to, since that was negative, it was less, to $3.58 more than in New York. So it gives you an idea of what that difference is and how big that difference is. And so I usually look at these numbers. It's not always less and more. Is in this case, is this one's negative and this one's positive. If they were both negative, it would always be less. If they were both positive, it would always be more. In this case, it's not. I do want to point out that 0 is in this interval, so it could be that that mean difference is 0, which means I could have also done my hypothesis test from this. So I could have actually found from the confidence interval the results of the hypothesis test. I could have said, just running the confidence interval, hey, 0's in this interval, so I have no evidence that there's a difference. If 0 is not in this interval, then I do have evidence that there's a difference.